this chapter we will be studying the transformations of functions. In this lesson we're going to look specifically at reflections over the x-axis and the y-axis.
So a reflection is a transformation, okay, and it says here that reflects a graph in an axis. Now it doesn't even have to be an axis, it could be in a line, it really doesn't matter, but for the most part in this particular course it's going to be about an axis. But what a reflection does is it changes the orientation of a graph. It doesn't change the overall shape, just the orientation of the graph. And really, we call it a reflection because the result is really like looking in a mirror. Okay, it's like looking at the mirror image of a graph across the line. And so if you have both of those graphs together, that line becomes this line of symmetry, okay? So any points where the function crosses the line are going to be invariant. It's kind of like if you thought about your reflection in a mirror. If you were to reach out and touch the mirror, basically that point of contact there, if you would think of it this way, is right on the mirror. It's not really reflected, it's right there in contact with the reflective surface, okay? It kind of stays stationary, but everything else, the further away you are from the mirror, the deeper your reflection looks in it. So anyway, so like it says up here, changes the orientation of the function. Now, the reflections here are all related to the negative sign, okay? And as such, that sometimes makes these things kind of hard, okay? Because we all struggle every once in a while with how negatives affect functions here. So a vertical reflection is going to be reflection in the x-axis. That's your mirror here. Now, for some people, that's a bit hard to get your head wrapped around because you tend to associate the word vertical with the y-axis, and that's true, you should. But for example, this is a picture of a reflection of the letter R, and it's vertical, okay? Because notice that the positions here, all the vertical positions are flipping, okay? They're all changing. So this thing is standing on the x-axis, and when you reflect it over the x-axis, it's now going this way. That is a vertical change here, but it's over the x-axis, okay? Now, the way we do this, and this is the information that we really want to focus on, so let's zoom in a little bit here. Actually, I'll do it like this. So here's our function, if you will. We start with our original. It's like this R right here. And what we're going to do is we're going to replace all of the y coordinates with negative y. We're just going to change all of the signs. Now, in the function, that looks like this. Our y equals f of x becomes negative y equals f of x. And then we would bring that negative over. And the negative sits outside the front of the function. And now in this case here, the mapping is extraordinarily simple. It really is, because it's basically exactly what you would want it to be. The negative on the y just becomes a negative and on the y. I mean, that's all it does. It doesn't do anything weird like we saw with the translations here, where if it was a horizontal translation, you saw like a negative in there, it actually meant the other direction. Okay. Now let's zoom out again and take a look at the horizontal horizontal reflection. In this case, this is over the y-axis. That's where our mirror occurs. And again, I know that causes people some difficulty to get your head wrapped around, but when you make a horizontal move here, when you flip this thing horizontally over the y-axis, okay, it's because this is the thing that you're flipping it over. It's a horizontal move, even though we associate the word horizontal with x, the x-axis. Really, the thing that stays the same here is going to be anything that would be on the y-axis. We're going to flip it over here. So let's take a quick look now at these pieces. We start with our original here, and this time, okay, if things are going to flip over the y-axis, it's the x-coordinate that changes. So we're going to change the x to negative x, which means in the function, we put a negative in front of the x in front. Okay, this goes in with the independent variable. And it does the exact same thing on the image point. The independent variable has the negative in front of it. Okay, so that's really all you got to do. It's quite simple. The only hard part here for people is going to be remembering, okay, that if it's a vertical reflection, it's over the x-axis, but it's still vertical reflection. We're still changing the y from a positive to a negative, or vice versa. Horizontal reflection, we're still changing x with negative x. But the description of it is it's a horizontal reflection over the y-axis. Other than that, everything else here works really nicely together.
Given y equals f of x, complete the table and graph the following. Identify invariant points.
Okay, so we can see right here that this is going to be a horizontal reflection. Okay, the x-coordinate has changed, the independent variable has changed here. So, and we've seen above here that that simply means putting a negative with the x. Now, that means changing the signs here. So, negative 5, 6 is going to become positive 5, 6. Negative 2 becomes positive 2, negative 2. Now, here is where hopefully you'll get a sense of why the invariant or why this is considered a reflection over the y-axis here. This point right here, 0, negative 2, is going to be on the y-axis. Okay, now when you put a negative in front of 0, nothing happens. Okay, negative 0, positive 0. 0 is neither positive or negative, so it doesn't react to that. So this point stays the same. Here's our invariant point. Okay, this one here is invariant. Now, 2 comma 0 is going to become negative 2, 0. Okay, in this case here, because we're not doing anything to the y-coordinate, that was irrelevant. It was just the x-coordinate that changes. And then this became negative 3 comma 1. This became negative 5 comma 0. Once again, yes, there's a 0 in there, but it's on the wrong coordinate. So that means this point right here is going to be invariant. Everything else is going to change here. So this negative 5, negative 6 became positive 5, positive 6. This negative 2 is going to become positive 2, negative 2. This one stays the same. This point over here at, what was it, that was 3, 1 is going to become negative 3, 1. And this point here at positive 5, 0 is negative 5, 0. So now we can connect the dots here. This is going to come over to there. It's going to bounce up to there. And that's going to connect to there. Okay? So you can see how that thing has just flipped.
Graph the following reflection and identify the invariant points.
So in this case, the graph is a little simpler than the previous one, so we don't really have that whole table of values to fill out here. Notice that the negative is in front of the function. Okay, this whole thing is the dependent variable, that's my y. So this is a reflection over the x-axis. And again, I know that's the hard part here. So the invariant points will be anything that's on the x-axis. Well, let's just take a quick look there. That's going to be the point negative 3 comma 0 and the point 1 comma 0. And again, the reason why those are invariant is because if you were to throw a negative in front of those y coordinates, it wouldn't change anything. And so that's why the x-axis becomes that mirror, if you will. Now we can go over here and graph this. And actually, it's relatively simple because I know these 2 points are going to stay the same. I know this point right here is going to reflect over. So the x-coordinate stays the same, but the y-coordinate at 2 is going to become negative 2. Now really all I got to do is connect the dots to get a sense of what that's going to look like. And that's what that graph is supposed to look like.
Given that the point negative 5, 4 lies on the graph of the function y equals f of x, state the coordinates of the corresponding point and the type of reflections.
Okay, so this should be a pretty straightforward question to do here because all we're doing is playing with negative signs. So let's take a quick look at this one right here. The negative is in front, meaning that x comma y is going to become the point. Well, when it's in front of the function, this refers to the dependent variable, so it's the y that's going to change signs here. So I take a look at my point, negative 5, 4. And I know that just the y coordinate is going to change signs, so it's going to become negative 5, negative 4. That's my new point. For this second one here, x comma y is going to become the point. Well, again, notice that the negative is in front of the independent variable, that's the x, so that's going to happen on my point as well. That's one of the beautiful things about this is that what you're seeing in the function in this particular case really does just happen on the image point. And so negative 5, 4, we're changing the coordinates of x, so this becomes positive 5, 4. And then over here, oh, here we go. Here's the big one, x comma y. Notice that both of them are changing here, so negative x, negative y. So negative 5, 4 will become the point, positive 5, negative 4. That is a reflection, or that is reflections over both of the axes.
Given the point negative 3, negative 6 lies on the graph of the transformed graph y equals f of negative x, state the coordinates of the corresponding point on y equals f of x.
Okay, now I hope you recognize this question from discussions that we've had previous to this. We are told here that this point lies on the transformed function y equals f of x. So we went from y equals f of x, it lies on the transformed f of negative x. So we've got this point here, x comma y. Okay, when the negative is on the x here, that's a reflection over the y-axis, but the image point retains what I'm seeing in the function, so negative xy. But the point is on this one. So let's take a quick look at this again here. So x comma y, again, is becoming the point negative x comma y, and this is the point negative 3 comma negative 6. Well, notice that the y-coordinate stayed the same, so I know this is still going to be negative 6, but the x-coordinate became negative, meaning that the original one must have been positive 3. That's the point that we were looking for. That's the point that we were looking for. 3 comma negative 6. That's the answer.
Given the function f of x equals the square root of 3x minus 5, write the equation of the transformed functions.
Okay, now a question like this is really just requiring you to be very comfortable with the description and function notation. So we're going to reflect this function in the x-axis. In the x-axis means a vertical transformation, okay? So a vertical reflection. So the negative goes in front of the f of x. Now, here's where you got to be really careful. F of x, okay, my function notation refers to both of these two terms here. Not just the root of 3x here. So just putting the negative in front of that first term is not enough, because there is more to f of x than just that first term. Now, once that's done, I need to distribute the negative to both of those terms, and I get negative root 3x plus 5. So it's not just a change in that first term, okay, and a lot of people will get confused by that, but it's a change in both of them. In fact, that's how I can recognize very clearly that this is a vertical reflection on that function. Now, if I reflect it over here in the y-axis, that is a horizontal reflection, which means what I've done here is change the x to negative x. In my function, I'm going to replace the x with the negative x. This is the square root of 3 times negative x minus 5. And then this is going to become, well, there's really not much I can do with it other than multiplying the 3 by the negative x to get negative 3x minus 5. Now, there's no problem having that negative inside there, because what will happen here is the only values of x that I will be allowed to use will be negative ones. Because as soon as x becomes negative, when I multiply that by negative 3, the result will be positive, and then I can take the square root of that. You might be tempted to think, well, I can just take the negative out, but actually you can't, okay? Because in order to take a number out of a square root, I would have to, or a radical like that I should say, I would have to take the square root of it. And I can't take the square root of the negative, not and expect to get a real result, so I got to leave it in there. So that is the best I can do in this particular question.
Describe the following transformation of y equals f of x and sketch the graph of y equals negative f of negative x minus 1 plus 2.
Okay, so what we really got to do to answer this question is really focus on what we're being told here. Okay, well, I can see right now that there has been, I'm going to look at my image points here, okay, I can see that there's been a vertical reflection. Okay, the y has changed to a negative here. I can see that there's been a horizontal reflection. Okay, there's a negative in front of the x. But there's been a horizontal translation, 1. Now think about this. What would I do to get x by itself? I'd add 1. So this is 1 to the right. And there's been a vertical translation. Okay, look at that. The y has been isolated, and what's way over here is a positive 2. So I added 2, so that means 2 up. So my point is going to look like this. What have I done to the x? Well, I've made it negative, and then I've added 1. Okay, what have I done to the y? Well, I've made it negative and then added 2. So these are my image points here. So now I'm going to do these things kind of step by step. So let's take a quick look over here. Now bear in mind, sorry, I should talk about this before I go over to the graph here. Bear in mind that multiplying by the negative in front of both those variables happens before I do the translation. Now, let's take a look at the key points here. This point right here, okay, 0, 0, and actually what I'll do is I will list this off here because I'll make this easier for myself. I'm pretty lazy. So I'm going to make this negative x plus 1 comma negative y plus 2. So first of all, let's take the point 0, 0. The negatives will do nothing here. So under the reflections, this point would have been invariant. But I would add 1 to that, and I would add 2 to that. So that's going to become the point 1, 2. I've got this point right here. That's the point, what is that? It's going to be 1, 2. Okay, so it becomes negative 1 plus 1. It's going to be 0. Negative 2 plus 2 becomes 0. Okay, so that point is going to drop down, and that's going to move over to the origin. The next point that I've got here is the point 0, 2. Well, negative 0 is just 0 plus 1 is 1. And I can't believe I just did that. I am so sorry. Ugh. Obviously, I need a little bit more caffeine. So that was the point 2, 0. My mistake. I am so sorry. Negative 2 plus 1 is negative 1. And then negative 0 is just 0 plus 2 is 2. That was that point right there. Now let's take a look at this one. And I better really be careful here. 1, 2, 3, 1, 2. So 3, negative 2. Plug that in. Negative 3 plus 1 is negative 2. Negative of negative 2 is going to be positive 2, plus 2 is 4. And then I got this last one over here, and this is the one I screwed up, the 4, at least the same idea. So 1, 2, 3, 4, that's 4 comma 0. Okay, so negative 4 plus 1 is negative 3. Negative 0 is just 0 plus 2 is 2. So here are my points, and now let's just plot these points here. So the point 1, 2, okay, 0, 0 became the point 1, 2. That actually goes right here. Then I get 0, 0. Negative 1, 2, so negative 1, 2, negative 2, 4, negative 2, 4, 4, was it 1, 2, 3, 4, and then negative 3, 2. Negative 3, 1, 2, 3, 1, 2. Now all we really got to do here is just connect the dots. So my starting point was here, and this thing is going to kind of flip around like this, go back up, and down like that. Yeah, hopefully you get a sense of what's going on here. So you can see how that thing was reflected, kind of reflected, okay, over both axes, and then moved over into that final position right there.
If f of x is equal to 5x plus 2, then g of x is equal to negative 5x plus 2 is a reflection of f of x over which axis?
Okay, now this one can be really confusing here, okay, because notice what's going on here. I've got this f of x is equal to 5x plus 2, g of x is equal to negative 5x plus 2. I can see this negative up front here. Don't fall into the habit of immediately thinking that because there's a negative in the front, that is necessarily a reflection over the x-axis. In other words, a vertical reflection here, okay? Let's talk about what's going on here. Let's just say, for example here, let's say this is a vertical reflection. So y is going to be replaced with negative y. So then what happens in our function is we get negative y is equal to f of x, or y is equal to negative f of x. Now here's the issue, okay, the problem that we have in a lot of cases here is that f of x refers to, in this case, 5x plus 2. There are two terms in that function. And so when I plug that negative through, I have to distribute it to both terms. So right here is what a vertical reflection, okay, a reflection over the x-axis would look like. Well, that's not what this looks like. So this cannot be a reflection over the x-axis. Now let's take a look. What would reflection over the y-axis be? Well, a horizontal reflection, I would replace x with negative x. Okay, so in my function notation, this becomes f of negative x. And so in this particular case here, that would be 5 times negative x plus 2. And when you multiply the 3, you get negative 5x plus 2. Now notice only that first term has changed. Only that one term with the independent variable in it, the x, has changed signs. Compare that to what I got. There's my g of x. That's exactly what I get here. That is a reflection over the y-axis. Actually, just for fun, let's talk about what would have happened if it was reflected in both the x and the y-axes. So if we put a negative in for the y and put a negative in for the x, okay, whoops, notice what would have happened here. Okay, this would have become negative 5x plus 2. Now I'm just going to do this, and I can do this in kind of whatever order I want here, because in both cases I'm multiplying by negatives, and so it doesn't really matter. Now I would divide, and the negative here will cancel, and I would be left with negative 2. So in this case here, again, only one term changes sign, but it's the one without the x, and that's how you would tell that this was a reflection over both axes. In this particular problem, though, again, it was just the y-axis that was the line that we reflected over.